So today we're going to do something I'll say a little bit interesting, and you can say that it's kind of related to algebra. Not totally about calculus, but it's definitely part of something that you see in calculus, which is known as sequence and series. So first, we're going to do the following. We have already known that, suppose that this is true, okay? We know that the sum from of 1 plus 3 plus 5 plus all the way to 2n minus 1, which could be expressed in the summation notation for k starting from 1 to n of the terms 2k minus 1 will be equal to n squared. And also we have the tools, the three tools that we have here, which will be the first n terms of 1 n together, which is equal to 1, which is equal to n, which makes sense because we're just adding n copies of 1s together. Next, we're going to add up the first n terms of the natural numbers, meaning that we're starting from 1 plus 2 plus 3 all the way up to the nth term, which is n. And the results will be in the following expression: n times n plus 1 over 2, but we can also rewrite it as two terms, the square term and the linear term. Good. We also will use the following tool, which is the first n, the sum of the first n square terms. So the results will be here. And if you don't know how to get it, you can just go to find other videos, from other math channels. They have already shown you how to actually get these results. So as we already know the fact that if we add the first n odd terms together, and again you can just check that this expression is always going to give us odd number, and as we don't skip any natural numbers of n, we'll be able to get all the first n terms, all the first n odd terms. So we are saying that adding the first n odd terms together will just end up with the result n squared. Here is the question of the day. Can we find such a sequence so that what we call here is called the partial sum of the sequence is going to give us n cubed? So before we move on, you can just pause the video and try it yourself first. Then we're going to figure out what we can get, or what the results would be. And again, you can use the tools up here to help you getting the expression. So our goal here is, again, is to find the expression of the nth term, or you can call it an, in this sequence, such that the partial sum of the first n terms will actually end up with n cubed. All right, and of course we need to follow a few rules. We're only thinking as polynomial expression. We are not going. We'll always start off with 1, and we're not going to use any other functions such as the exponential function or n logarithmic function in our expression to get some string values. Okay, so are you ready for it? Here's what we're going to do. So as we already have the three tools, we can actually try to use the tools that we have in order to generate what we want. So if we look at the third tool, which is the first n, the sum of the first n squares, we actually get from 1 all the way up to k squared, we have 1/3 of n cubed plus half of n squared plus 1/6 times n. So since our final goal is to get n cubed, and this term starts with this expression has n cubed, and in fact n cubed is the leading term in this expression. But the leading coefficient is not 1, which is what we need. Instead, we have 1/3. We can just try to get rid of the 1/3. How so? Of course, we're going to divide by 1/3. Or, in other words, we need to multiply both sides by 3, so that on the right-hand side, the 1/3 in the leading coefficient will cancel with the 3 to end up with n cubed. Then if we multiply everything in, we get 3/2 of n squared plus 1/2 of n. Now on the left-hand side, we're going to multiply this thing by 3. But since 3 is a constant, we can distribute it into each of the terms in our sequence so that we can rewrite as starting from k equals 1 all the way up to k equals n. And for each term, the expression will now become 3 times of the original. So we have 3k squared. Good. So now we already get the n cubed term that we want on the right-hand side. But we cannot call it the n yet because, again, we still have extra terms. How should we do it? Again, we need to subtract it if we don't want it to happen, or multiply by 0. But if we multiply by 0, we'll even get rid of the n cubed term that we want. So this is not going to work. So the other way, which is the only way that we can do, is to subtract whatever that are remaining. So in order to subtract the remaining terms, it is always better to start with the second highest term or the highest term of the remaining part, and then trying to reduce it one step at a time. So our second highest term here will be the n squared term. So in order to get rid of it, we need to subtract by 3/2 of n squared. So let's see what tools we can have. Well, we have already used this tool, and it would not be a good idea to use it again because this will also generate the n cubed term, which is already fixed in our problem. So this is no good. Then what can we do with the remaining tools? This one has the n squared term, and n squared term is actually the leading coefficient, is a leading term in this expression. So let's try to play around with this formula, and then we'll be able to hopefully get rid of the n squared term. But if we look at the expression carefully, here we only have 1/2 of n squared. And since we want to subtract 3/2, what can we do in order to bring it into 3? Of course, we are going to multiply both sides by 3, so that if we're going to multiply both sides by 3, the right-hand side will become 3/2 n squared plus 3/2 n. And don't forget, if we multiply the right-hand side by 3, we need to do it on the left-hand side as well. So our expression will become 3 times the summation. And again, 3 is a constant. We can distribute into the sequence or each term without changing the actual value of it. So we end up with the sum of 3k. And again, now we want to subtract it. So once we subtract it, we'll be able to cancel out the n squared term to end up with 3k squared minus the sum of 3k, which is going to equal to n cubed, and then the n squared term has cancelled out, so we only end up with the n term left. So we have 1/2 of n minus 3/2 of n. So we end up with negative n, or minus n. So we're not done yet. We still have the n term. What are we supposed to do? Well, look back to the tools. We still have one more expression that haven't used yet, which is this one. We can also try to use this to help us get rid of the n, because on the right hand side, n is the leading coefficient. And if we do so, all we need to do is just subtract this thing, then it will be, no, we have minus n. So to do so, we need to add this thing so that the n will be able to cancel out. So this gives us the final expression. We have 3k squared minus 3k plus the sum of the ones, so that on the right hand side we will actually end up with n cubed. And since this is finite, and again, when we say finite, it means that there are only finitely many terms here. It doesn't go to infinity. So we will say that if we choose some specific number for n, there are only n terms in total in the sequence, so that when we add them together, it will still be some number, not going to diverge or becomes infinity. So because of that, we are allowed to add them together and put them together inside of our summation to get our expression. And therefore, what is the expression of the a_nth term? Of course, in terms of n, such that this sum of the first n terms is going to give us a cubed. This is what we have. All right. So this is not it. I'll pause the videos here, but we still have actually one more thing that we can talk about in this expression. And in fact, in our next video, we're going to see a more general expression and try to use a different method to see how we can, or why we will be able to get such an expression of an, so that we can always guarantee to get n to the third power, or n squared, or n to some higher power. All right, I'll see you guys in the next video.